Hi everyone. Addressing your feedback from today's lecture of an introduction to thermodynamics. Um, First question I got was, what is Gibbs free energy? So yeah, maybe I don't think I gave a clear enough explanation. Um, in essence, if you have a substance, that substance's free energy, or what we sometimes specifically call its Gibbs free energy, is the portion of its energy that you can use to do work. So we talked about in first semester a little bit, we talked about heat exchange as one way of transferring energy. Another way of transferring energy is through work. So heat is like a microscopic transfer of energy. If I take two objects that are at different temperatures and they touch together, you have heat flow, and that transfer of energy happens at a microscopic scale. Particles over here are moving really fast. They knock into slow-moving particles over here and make them move a little bit faster. And so you have a transfer of kinetic energy from a hot object to a cold object in the form of heat. Work is a macroscopic transfer of energy. Like I'm just picking something up here. If I have an object and I lift it up, I have to spend energy to change its potential energy and lift it higher. I have to overcome the force of gravity, and I have to spend energy to do that. That type of macroscopic, ordered transfer of energy is called work. Free energy is the idea that when I try to get energy out of a substance, I can't actually utilize all of it as work. So case in point, if I have a bucket of gasoline or a gallon of gasoline, and I want to use that gasoline to do work, like say I want to burn it to get some thermal energy out of it, and then I can use that thermal energy to say heat. I'm sorry, I'm thinking of something very convoluted here. So I have gasoline. I burn the gasoline and I heat up a pot of water and turn that into steam, and then I can use the steam to say run a steam engine, where like they have a series of gas containers which expand and contract, and those contractions and expansions allow you to do work. Now, all of that process originally comes from the energy of your gasoline. Your gasoline is some type of hydrocarbon. It has energy stored in its bonds, and when you react that gasoline with oxygen, you produce CO2 and water, and you could use the energy of this process to do some quantifiable work. But in practice, you can't utilize all of that energy. You can't direct it all into work. Some of that energy that you will release when you do this process, some of it is inevitably lost as heat. Like if I'm trying to heat up a pot of water on the stove by burning, say, propane or some gas, some type of natural gas, okay, some of the energy goes directly into the pot, but some of it dissociates out into the surrounding atmosphere, and so there's heat loss there. I can't efficiently take use of all of a substance's energy. Some of it is inevitably lost to the surroundings, lost as heat. What we call the free energy of a substance is how much of that energy, a portion of a substance's or an object's energy that can be utilized to do work. So that's a very much a thermodynamics perspective, like an old school thermodynamics. Thermodynamics was originally developed in order to make more efficient steam engines. So a lot of the language and thought processes behind thermodynamics are from the perspective of trying to make things more efficient, getting work out of something, converting heat into work. That's sort of the language of thermodynamics and the perspective that thermodynamics takes. But free energy is the idea. Basically, free energy is the idea that not all of a substance's energy can be utilized to do useful work in a directed fashion. Some of it inevitably is utilized to increase the entropy of the universe. The energy spreads out naturally. You can't direct it all into work. Let's see here. For the entropy change of a solid going to a liquid, is the entropy change for that always positive? Are there any exceptions? I was thinking about this, and in general, no, there are no exceptions. Again, if you have a pure substance and it's converting between different physical states and it's not undergoing any chemical reactions, you just have solid ice converting into liquid water, that does have an increase, a positive change in entropy. And that's going to be true for basically every substance. There are no exceptions to that. And along those lines, I had a similar question. Do phase changes to gases, are those generally, do they use those generally in, oh, no, actually I should clarify. This is a slightly different question. I had a question of if you're going from a liquid to a gas or from a solid to a gas, do those changes generally imply an increase in energy or enthalpy? Or does the enthalpy necessarily increase when you undergo these physical changes? If you are going through a physical change, so let's say I have liquid water going to liquid gas, that enthalpy change, that energy change is always going to be positive. Because you need to, if you're going from a liquid, so you have some disordered collection of molecules, and you're going to a gas, so I have a collection of magnets here. Those magnets, just like real molecules, they have intermolecular forces that keep them together. And if I want to turn them from some type of condensed liquid phase into a gaseous phase, where everything is separated from each other, I need to spend energy, I need to supply energy and overcome intermolecular forces. So if you're going from liquids to gases, or from solids to gases for that matter, yes, you will always have an increase in energy. Again, that's only for a physical change, though. There are examples of chemical reactions where you go from solids to gases, where those will, I'm trying to think actually now that I think about it. Yeah, okay, I can do an example up here. Liquid gas or liquid propane. You're starting with liquids, you might have some gaseous oxygen, but you end up with a bunch of gaseous products. And that's going to have a net decrease in energy. So chemical reactions, they aren't necessarily always going to have an increase in energy going from liquid to gas. There are other factors to consider. Is entropy related more to geometric configurations, as in like molecular configurations, more so than the energy required to break bonds? Yeah, generally I would say that there's no direct correlation necessarily between a substance's energy and its entropy. Entropy is very much so a statistical thing. Number of permutations, how chaotic it is, how random it is, how many different ways there are of doing things, how many different ways are there for me to arrange the atoms in a molecule. No real bearing on the energy of those bonds. There's a little bit of correlation, but it's subtle enough that I would say it's beyond the scope of a general chemistry course. Something that you might touch upon in a dedicated thermodynamics class. You might discuss some of that relationship. But yeah, generally I would say that the entropy of a substance is more related to its molecular or its geometric configurations, its molecular geometry, the number of atoms in a molecule. Molecules that have more atoms in them inherently have more entropy, molar entropy, than a substance that has relatively few molecules per mole. So I would say that that's the case, that it's not necessarily related to the energy required to break the bonds between molecules. In class, with your dropping ball example, you wrote delta E. So I had this example, and I said, okay, E initial and E final. That's not a very good I there. And I said delta E is equal to E final minus E initial. Is that delta E the same as delta G? I don't have a delta G up there, but is this the same as delta G? And generally, no. We will frequently hand-wavingly make that correlation. We'll say that something has a drop in energy when we really mean it has a drop in free energy, and vice versa. But in general, the two are not related to each other. Sorry, I dropped my marker cap here. Free energy, I will say there's such a thing as just generally energy. And that's kind of the discussion I'm having up here. Free energy is a concept that comes about when you have lots of particles and you're talking about the sum total of all of their energies. So this might be the energy of like a single object. Free energy is a statistical measure of all of the energy in a large system and how much of that energy you can extract as work. So they are not equivalent. I would say that they are not equal to each other. So yeah, if I'm ever talking about like a single substance changing, I'm probably just talking about its individual energy. If I'm talking about like a chemical reaction where it's implied that you have several moles of substances reacting together, that's when I would talk about the delta G of a substance. So here's a question. Does the least amount of order in something equate to a decrease or an increase in energy? So that's I would say my initial response to this question is no. There's no correlation necessarily between entropy and an energy change. So no, I would say that the least amount of order does not necessarily mean that something is increasing or decreasing in energy. What is the definition of a microstate versus a macrostate? Are macrostates how we assess which options make up the greatest possible number of outcomes? Okay, so generally, let me give you a general definition here for what I mean when I say a state. So state, in its most basic conception, is just a particular configuration of properties. So you could talk about like a quantum state being in like the lowest energy state, or being in a p orbital, that's like being in a p state. A 3px state, the electron is falling, has a particular configuration of quantum numbers. That might be its particular configuration of properties there. So that's just generally what I mean when I say a state. Your state could be like your GPS coordinates, like what is my longitude and latitude at any given time. That collection of numbers, your longitude and latitude, that might be your positional state. In the context of this of thermodynamics, a macro state, a system's macro state, refers to the value of its macroscopic properties. So it's the configuration, I guess, of Macroscopic properties, things that we can actually measure macroscopically. So that's going to be something like the number of particles. I mean, we can measure moles of particles, and we have Avogadro's number, so we can actually count the number of particles macroscopically. The volume of a system, the temperature of a system, the pressure, those are all considered to be macroscopic properties. So at any given time, say a gas has a certain number of particles, a volume, temperature, and pressure. That collection of numbers, we would say that is the gas in a particular state. So I could say, well, the gas has a volume of 1 cubic meter, and its pressure is 1 atmosphere. Its temperature might be 298 Kelvin. And let me see, I'm not going to do the gas law calculation really quickly here, but point being that there should be some way to predict the number of particles that it has. So that is this collection of numbers we would call its macro state. Now, within this, for this particular macro state, there are several, in fact, I would say there are many possible microstates. And in this case, microstates, a microstate gives you the configuration of the microscopic properties of a system. Things that you can't actually measure exactly because the particles are too small. So microstate, the microscopic properties of a system might be the positions and the velocities. I apologize for doing this at an angle. Might be the positions and properties of the particles in that system. So this might be one particular macrostate. I'm sorry, this is one particular macrostate, and this might be one microstate of that particular macrostate. But at some later time, so imagine these boxes are the same volume. Imagine that I don't do anything to I have a gas and it's in a box, and I don't do anything to the box. Or like imagine that at one particular second I take a snapshot of the box. So I know its volume, its pressure, its temperature, and the number of particles. But over time, if I look again, it might still have the same, do I have, what is it, 6 up here? It might have the same volume, again, if I had drawn it correctly, same volume, same pressure, same temperature, same number of particles, but the particles have changed positions over time. And maybe they've collided with each other and they've transferred some kinetic energy between each other, so their velocities are slightly different. So these are two microstates which are both in the same macro state. They both have the same velocity, temperature, pressure, and number of particles, but they have different positions for the particles, and the particles have different kinetic energies. They might have just redistributed their energies. So that's the difference between a macro state and a microstate. And generally, so for instance, let me think here. If I were going to talk about, yeah, that's what I will say. I don't want to go off on too much of the tangent here. So that's the difference between a macrostate and a microstate. I hope that answers your question. If it doesn't, please feel free to stop by during office hours. I would be happy to discuss that in more detail for people. But yeah, very generally speaking, we think of a gas as having many, many more microstates. I'll go off on a little bit of a tangent here. The gas has significantly more microstates because there's lots more ways I can rearrange these particles as opposed to a solid or a liquid. So imagine you actually, let me even make this more precise. Let's say this is a liquid here, and let's say it's got the same number of particles as these guys do. These guys each had 6 particles, and there's my 6 particles. If it's in a liquid or in a solid, they all have to be tightly packed against each other. And that limits the number of possible configurations I could come up with and still be describing the liquid as having the same volume, temperature, number of particles, so on and so forth. So in general, solids and liquids have fewer microstates, fewer possible configurations than gases do. So this would be a gas, this would be a liquid. And that's how, since we define entropy as the maximum, as related to the number of microstates, that implies that gases have a higher entropy naturally than liquids do. So people in the 8 a.m. section, I realized I wrote this up as K, and I didn't actually explain what K was. Again, we're not going to calculations with this, but for people who still want to be familiar with the equations, K is called the Boltzmann constant. It's named after Ludwig Boltzmann, who did a lot of the original theories on statistical thermodynamics and came up with this expression, or derived this expression. The Boltzmann constant actually has the value of the gas constant, that is the ideal gas constant, over Avogadro's number. So it's just another set of constants combined together. Okay, so that's it for this feedback video. Again, if you have questions, I will be very happy to address them either via email or in person in office hours. Or, again, I have an open door policy, so you guys don't have to come in exactly during office hours. I'm always going to be here, or I will usually be here. Anyway, I will see everybody on Friday. Take care.